Okay, so I just wanted to give you a little extra help with this NMR stuff because it is pretty tough. Even this video could probably be, I could have a supplement to this video. So I'm going to go through, give you as much information as possible, but basically what I'm going to be doing is just running through problems. And then along the way, I'm going to either give you my thought process or I'm going to give you some fun facts or some tips and tricks. Okay, so 59, for example, C59. This is a specific question. I know I did a little shout out to everybody telling you, let me know what you want me to cover because I'm going to do some problems. So these two, 59 and 65, are very specific questions. And so the rest of them are my own thoughts. Okay. Let's see. Compound A. So this data is given to you, and you're supposed to figure out the structure. So this right here tells me a carbonyl group. Okay, so that you should just know, right? And then the proton NMR data is also pretty straightforward as well. So this, we have a 2.15. We got a singlet with 3 hydrogens. 3.7. We got a singlet with 2 hydrogens, and then 7.2 broad singlet with 5 hydrogens. So what screams out, the thing that kind of tells me exactly where to start, I guess, is, that's a very bad way to put it. The thing that screams out to me the most is basically this right here, this 5 hydrogens in the 7.2 region. So what that tells me is I have a substituted benzene ring. And what I mean by that is I got this benzene ring, because it's in that 7.2 region, that's super far downfield, and so that's telling me that that's probably a benzene, and it's got one thing on it because there's 1, 2, 3, 4, 5, right? So if it were 4, then we would say, okay, well, we have 2 things on the benzene ring, and then the multiplicity would be what's kind of telling us what the type of substitution it is, right? So is it here, or is it here, or here? Okay. Okay, so now we know it's a benzene ring with something on it. We know it has to have a carbonyl group. Okay. Oh, you know what? The formula is also C9H10O. So this is accounting for 6 carbons. So we need 1, 2, 3 more carbons on there, and we know it can't come anywhere else off the ring, and we know we have to have a carbonyl group. So that's just the initial thing that I propose. I'm going to take a look at the rest of the NMR data to help guide me, either make sure that carbon connectivity is correct, which it has to be, or and then also see where that carbonyl group goes, because technically we could have it here, here, or maybe here. That's not the best option, and because you would have an aldehyde when we'd have an additional resonance, but so that leaves us with the 2 internal ones. This right here says 3 hydrogens with a singlet, and then this is also 2 hydrogens with a singlet. So that automatically tells me I have to have that carbonyl group in the middle, because this and this are not close enough to couple with one another. This has the 2 hydrogens, this has the 3 hydrogens, and they're both singlets. I noticed I didn't even pay attention to this and this, so I would take a look at that after the fact to make sure that it makes sense. Okay, so this being at 3.70 and then this being at 2.15. So this was a problem for the student that they asked me this question. It's like, what's up with this chemical shift that's really far? But it is a benzylic proton, so it's next to that benzene, and then it's also next to the carbonyl group, so it's going to be shifted a little bit more downfield compared to the normal benzylic, or maybe the normal alpha carbon, right, or alpha CH2. Okay, so but everything else checks out, right? And that's the most important thing, is like, okay, well, the multiplicity checks out, the bond connectivity therefore has to be good, and so we'll just accept that 3.7. I'll give you some info on how to kind of help with determining or approximating chemical shifts a little bit later in this. I wrote some stuff down ahead of time for it to make it easier to go through. So this one right here, I also said I would do C8H11N. Identify the structures. So I haven't gone through this, so this is just real time. Notice this 5 hydrogens right here around that 7 region. So this tells me I got a benzene ring with something on it. I got 2 hydrogens here, 2 hydrogens here, and then 2 hydrogens here. So that's 6, 7, 8 with, let's just do, oh, you know what? Here we go. Let's do that. Because that has to be 2 hydrogens, that has to be 2 hydrogens, that has to be 2 hydrogens. So, oh, yeah. Let's check the IR actually. NMR is like super helpful for me, and that's usually what I focus on first, but does everything make sense? So 1603, 1497, that's the benzene ring. We want some CHs. We've got those. We also have our 2 stretches for the NH2. Everything seems to check out. We've got our 2 protons that are not coupled right here. So this is probably your NH2. We have what looks like a triplet here, and then what looks like a triplet here, and that's this set of protons and this set of protons coupling with one another. And so there you have it. That's the structure. Again, I didn't really focus on the chemical shifts. I actually just focused on the bond connectivity that would give us the right multiplicity. And so I think that's kind of the approach that I would suggest taking. I am only doing this one. Sorry, I'm not doing this one, but I believe in you. You can do it. All right, so let's cover homotopic and aneotopic or diastereotopic protons. So like, what's the deal with this? I'm trying to summarize this as easily as possible with what we know. And so each of the explicitly drawn protons are the ones we care about. So like these, and these. And so we're going to identify these as homotopic and aneotopic or diastereotopic. So the way we can do this is homotopic is going to be, it's going to have reflective symmetry and then also rotational symmetry. Okay. An aneotopic is going to have just the reflective, okay, reflective, and then this one's not going to have either one of those, okay? So what do I mean by that? Let's focus on this one right here. So if we look at this, and then if we rotate this molecule about that vertical axis, we will see that you can't really tell. Like if you close your eyes and then I rotated it or did not rotate it and I asked you to guess, you wouldn't know. You have no idea, right? And so that's what we mean by like rotational symmetry, right? So this has rotational symmetry just technically that automatically gives it reflective symmetry. But we usually, the only criteria that we need to meet is rotational symmetry. Okay. I just felt like we needed to do both and then go to reflective for the aneotopic and then neither for the diastereotopic. Okay. So, what does reflective symmetry mean? Well, what it means is, let's say we bloop, we wanted to draw a much better mirror than that, but we're not gonna, because we just gonna get down to business. My business. Okay. These are mirror images of one another, right? And that mirror image is essentially what reflective symmetry is. These protons are interchangeable by reflective symmetry. And so like if we were to now rotate this about that vertical axis, what we would end up with is this, right? And so that's really what we want. Another way to look at this is just in general to identify these. Is there a plane of symmetry, right? So we're just straight up cutting this molecule right down the middle, and that's giving us our plane of symmetry. Now, in antiotopic protons, they do have that plane of symmetry too, but it's reflective again, and it's harder to see. So this is what we mean by reflective, but that means that it does have a plane of symmetry, and it's tough to see again, but what you're doing here is kind of slicing the molecule in this plane, like in the plane of the board, okay? So this is going to be on one side, this is going to be on one side. This hydrogen atom that's here is going to be cut in half. This chlorine is going to be cut in half, and then each of these carbons is technically cut in half as well. But we would have the same thing on either side, right? So that's our symmetry element, and that's what makes those protons equivalent. And they are an antiotopic. Did I write that yet? Let me write that pretty in pink. This one was homotopic. These are an antiotopic. Now these ones don't have that symmetry that I was talking about, right? So what are you talking about, Jess? It looks pretty cool. Why is there no symmetry? I don't get it. Okay, so let's go here. So let's say we got that OH here. We can draw a little mirror image of it, right? Let's do that. Let's see how it looks. What it look like. What it look like. There we go. Okay. Everybody follow? Sweet. So that is a mirror image, right? But if we rotate about that vertical axis, what we're going to get is, you're like, oh, Jazz, it's the same thing. No, it's not. It's pissed. I'm about to be all up in that other molecule right now. Okay, so that's the difference. This right here, that's pointed in a different direction. So that mirror image is not, you can't rotate it and have it look the same, right? And so that's where we are lacking that symmetry, and therefore this is diastereotopic. So this is the easiest way I feel like I can explain these symmetry elements for homotopic and antiotopic and diastereotopic. There's definitely an easier way to me to identify these. For example, if you know something is chiral, a carbon with 4 different groups on it, if you have that in there, then your other CH2s are going to be diastereotopic. If you can substitute one of these hydrogens out for like another element, or another like D or Z, or like a Cl group, like whatever you want to do, as long as it's different, then that carbon would now have 4 different groups on it, and that makes it an enantiomer. Okay, and then homotopic is just the other one. It's hella symmetrical, right? So diastereotopic or diastereomer, this aspect of it, and then enantiomer, those are concepts that we'll learn in the next chapter, or in chapter 5. So that's why I'm saying, like, there's easier ways, but like what we know right now, that's the way we want to do it. And then that's still oftentimes the way it's explained, but I just find it easier to know what an enantiomer is and know what a diastereomer is. And then can you make it by substituting one of those CH2s, hydrogens, for a D or a Z or a Cl or something different? If you do that and they make an enantiomer or a diastereomer, then those protons are by definition enantiotopic or diastereotopic. Okay? Well, it's going to click, don't worry. Number of expected signals. So this is helpful this is definitely like in line with homotopic and anthrotopic and diastereotopic, because you have to know if they're equivalent, right? And so this is the symmetry of the molecule. You slice that right down the middle. So there's going to be one unique signal there. There's going to be one unique signal here. I feel like I should do them in different colors. I feel like it's going to take forever though. So there's these hydrogens, because of that symmetry, it's the green ones are equivalent. These are the CH3s. These are equivalent to one another. Let's see, we'll do pretty in pink for this bottom one, and the poopy brown. We'll do poopy brown right here, just because that's what I got. Okay, so that's 1, 2, 3, 4, 5 different number of signals, or I would say proton resonances. So that's 5 total. Okay, so for this one, I'm gonna, just so I don't have to color code everything, I'm gonna say this is 1. So this one doesn't have that symmetry element anymore, right? Like we don't cut it down and we have the same thing on the left as the right, and so that's just because these are connected at different carbons with respect to that methoxy group. Okay, so that throws off the symmetry of this molecule completely. Now, we still definitely have that, like if we cut this molecule like this, like the enantiotopic example, where we're just slicing every atom in half and we're having this hydrogens on either side, then we still have that symmetry element. And so what that tells us is that these hydrogens are unique from one another, but they are still one signal. Like there's one blue signal and one red signal is what I mean. Okay. And then in addition to that, I'm not going to color code the rest, sorry. So there's 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's the number of signals. And I forgot to remind you, like, just please try these problems on your own. Like, you see the structures in front of you, right? Pause the video, try them on your own, and then see if your answer matches up with me. So 1, 2, 3, 4, 5. That's the number of signals because we don't have that symmetry element. There's 2 substituents on here that are different, right? So we can't just slice it through here and have the same thing on either side, but we can again slice it in that plane right there. Okay. So there's a hydrogen there, so that's 1, 2, and then 3. So since these hydrogen, since these right here, basically, long story short, by definition, these are these are diastereotopic. So these are different than these ones. That's obvious because like these ones are closer to the bromine, but they're also different from one another. So that's different than that. That's what makes it diastereotopic. And then this one is different than that one. So that's 1, 2, 3, 4, 5, 6, 7 proton resonances, right? Because there's this one right here that's hiding. Then there's these ones and this one. Cool. Think about it before you follow up on that question. Okay. 1. I gotta think about this one. So I want to just jump into it and say 2, 3, 4, 5, 6, and then 7. Those are different, right? So these are different because this is stuck. It's a double bond. It's stuck on that side. It's basically got a totally different environment than these 2 right here, or this one compared to that one. So we got 1, 2, 3, 4, 5, 6, 7. Okay. Hopefully you got the same number as me. If not, shoot me a question, think about it for some more before that, and then if you still don't get it, come to office hours, please. Let's see, chemical shifts. Okay, so this was like, it's not necessary, honestly. You saw me solve the problem up above without even focusing on the chemical shifts, but it would be nice to have this for some people. They really like to know, like, okay, why is this at 3.7, right? So if you have a CH2 or CH or CH3, then you can start with your 1.2, 1.7, or 0.9 as like a generic starting point. And then let's say we have like an alcohol group, right? Or we have an ester or a carbonyl group. Then what we can do is add 2.5 if it's an alcohol, 3 ppm or 1 ppm to if it's an ester group or a carbonyl group. Okay, so I guess this could be ambiguous. We're talking about this oxygen right here, right? So these protons right here. Okay, then if we want to know what that chemical shift is for, let's say just those ester protons that are just circled, then we would have our 3 ppm added to, since it's a CH2, our 1.2, and that gives us a approximate 3 point. Whoa, Jess, simmer down. Whoa, what am I doing? Yeah. 3 plus 1.2 is 4.2 ppm. And so this is definitely an approximation, okay? And it actually works pretty well. You're going to get fairly close. Let's see, what do we got here? So if we have, notice I wrote an alpha proton or a beta, then that's going to put it in a different spot. Okay, so that would put us at the alpha is what we were adding for the 2.5, and that goes for down here too. But if it's beta to it, like if it's one extra bond over, it's farther away from that oxygen, right? So that inductive effect is not having as great of an effect on it. And so we don't add as much, and so we would add 0.5 instead, okay? So that can be applied probably to this ester too. You're obviously going to have a little bit less of an addition for that one, but I don't have a number for you. And then it's probably similar, about a half, but again, these are just estimations anyway, right? So and then if it's just like a regular carbonyl group, like a ketone or something, holy moly, let's say like something like this, then we're talking add 1 ppm for there, or maybe add 0.2 for there, right? The alpha and the beta position. So hopefully that helps. If you're really wanting to have a closer prediction as to where these chemical shifts are going to be. Now, I did get a question about like what causes these chemical shifts, and it's really just about electron density, the way I view it. So if you have an electron withdrawing group, that's why you're adding 2 ppm, because then it's going to head further downfield. It's going to be more de-shielded, which means there's not as much electron density around it. And remember that electron density creates its own magnetic environment, and so that's basically the relationship between those electronegative atoms and their effect on the proton resonances. So if you have an electronegative group, it pushes to the left, aka downfield. And then if you have more electron density around a proton, then it's more upfield, okay? Or to the right. And let's see, multiplicity of each signal. So I thought I might go over this as well, just because. So we kind of need to be able to identify that protons are equivalent or not, right? First, so we can establish these are all equivalent. So what's the multiplicity of them? Well, there's no proton here, okay? So don't try and I think there's one there. There is a set of 2 here, but those are 1, 2, 3, technically the protons here. So that's 4 bonds away. Those are not coupling with one another. Okay, so these red ones would just be a singlet. And then there's 3, 6, 9 hydrogens. Okay, so anytime you see a singlet that's 9 hydrogens, you want to think this chicken foot right here. Bada bing, bada boom. Chicken foot is in the room. Okay, so these 2 protons right here, those are next to these gorgeous protons right here. And let's see. So those are, yeah, there's no, we don't have any weird things going on. We don't have any diastereotopic protons here. So basically, those 2 protons are coupling with the blue protons. And since it's 2, we have the n plus 1, right? So we have the 2 plus 1 equals 3. And this is the same. So it sees 2 protons that are equivalent, and then so we have the 2 plus 1 equals 3. So those are both triplets, okay? So we would just put a triplet, 2 hydrogens. And then we would do a triplet, 2 hydrogens for that one too, okay? Let's see, we do have a proton here. We've also got, I'm gonna put poopy brown ones here. CH3, CH3. So these are equivalent. They are both methyl groups. They see this pretty pink one, and since they see 1, we have 1 plus 1 equals 2. So these would be doublets, and it would show up as 6 protons because they are equivalent. They have the same chemical shift. Because if you rotate about this chemical bond right here, you can't tell what the difference is, right? Like again, if you close your eyes, rotate, close your eyes, rotate. Well, damn it, there's a little complexity to it, but I'll leave it. I think I might leave it alone for now. Let's just call it doublet, 6 protons, and then what do we want to do? Purple? Weird purple. Oh no, we're doing pink already. Jess, come on now. Pink. So this pink one right here, it sees 6 protons, right? So that is a 6 plus 1 equals a septet. Or 7. Okay, so that would just be a septet. You might abbreviate that as like sep, comma, 6. Oh, whoa, whoa, whoa. 1 hydrogen. Wow, why can't I do that right now? 1 hydrogen. Cool. Alright, so let's see if we can go through these faster. This right here sees these 2 protons, so that's going to be a triplet, 3 hydrogens, but symmetry of the molecule, you can see it straight up and down. It's the same thing on this side, right? So it'll still be a triplet because this still only sees these 2 protons on that side, but instead of 3 protons, it's going to be 6 total because we're counting for that side and that side. But the multiplicity is still the same. That's where people get confused. But each of these 3 protons, sets of protons, is only seeing 2 and only coupling with 2. Okay, so the same thing can be said for these. That's 2 hydrogens each. So I don't know why I started writing that. We've got those 2 protons seeing the 3 protons, and so it's going to be the 3 plus 1 equals 4, which is a quartet, and then it's 4 hydrogens because there's 2 sets of them. Okay, that's, let's see, there's a hydrogen here, so that's going to be 1, 2, 3 bonds away from there, so that's coupling. Okay, so this right here would be a doublet, and then it's 3 hydrogens, Oops, let me do that. I'll do poopy brown. Since that brown one couples with the blue ones, then the blue ones couple with the brown ones also, and that means that this sees 3 plus 1 equals 4, so it's a quartet, 1 hydrogen. Okay, let's see, that wasn't as fast as I had hoped. So there's 3, there's 2, there's 2, and there's 3. Okay, so this is going to be a triplet, this is going to be a quartet, this is going to be a singlet, and this is going to be a singlet. You got questions, let me know. So there's 3 here, there's 3 here, 3 here, there's 2 here, and then there's 3 here. Let's see, just quickly, there's a singlet there. These don't see anything. They're too far away, so those are also singlets. Those are also singlets. That is also a singlet, and that should be a singlet too, right? We don't have any chiral carbons, so that should be good. If I'm wrong, let me know. Maybe I'll give you an extra point. I'm moving through them pretty quick. So draw expected proton NMR. Okay, so this is where we're going to kind of couple our, or put together our knowledge that I've kind of gone over. So this is going to be a singlet. This right here is going to be, oops, I guess I can leave it there. That's going to be a septet, okay? Because there's 3 here and 3 here, which are actually doublets. So, but that doublet is going to be 6 hydrogens, right? This is going to be a septet, and that's 1 hydrogen. And that's a singlet, and it's 3 hydrogens. Okay. Now, where do they show up? So, these are the alpha protons that are coming off the carbonyl, remember? So, our baseline is 0.9, and then we can add 1 ppm. Okay, so that's about 1.9. Okay, we have a methine. That's what the 1 proton is called, a methine. The CH starts at 1.7 for our baseline, and that was, how far was that from the carbon? That's an ester, right? Coming off of that carbon adjacent to it, and so we're going to add 3 to the 1.7. So that's 4.7, approximately, right? I'm going to put approximately because this is not set in stone at all. Don't think that it is. Gets weird. So the CH3s, those, again, I didn't have them. Let's say they're, where's my 3? Did I mess up already? Did I use the wrong one? Oh no, 0.9. And then notice the beta proton here is like 0.5. And then the beta up from that carbonyl group is 0.2, so we can add somewhere in between there. Let's just add like 0.3 for funsies. So what was I at? 0.9. 0.9 plus 0.3, we'll go with approximately 1.2 ppm. Why not? Okay, we're totally guessing. And then the way it would look on the Proton NMR is, let's just do 4, 3, 2, 1, 0. And so we would have a singlet, or I'm sorry, a doublet at 1.2. So we go boom, boom, and then the doublet measure, that's in between. If it's a doublet, the 1.2 is like right in the middle of it. 1.9, we have a singlet, so let's just look like that. And then, what am I looking for? A single proton that is a septet at 4.7. So let's see, 1, 2, 3, 4, 5, 6, and then 7. That's so bad. This is not to scale. So like what I really want to do is actually shrink that. Oh no. But I can't now. So remember the area underneath the curve, like this area here, like if I'm calculating the area underneath all of these peaks, they should correspond to the number of protons. So this, if we did the integral of this and this, we would get 1 hydrogen, we would get 3 hydrogens, and then we would get 6 hydrogens. So like the area underneath this curve would be the greatest, and that's definitely not how I drew it, but I had to draw it just for the sake of you guys seeing what it looks like. Another thing is your numbers aren't always going to show up perfectly as like 1 or 3 or 6, right? Sometimes if you integrate it, it could show up as, this is also going to be a very nice looking number, but it could show up as 0.5, 1.5, and then 3. Okay, we can't have half of a proton, right? So we would have to at least multiply it by 2 to kind of normalize it to get to the 1, 3, 6. But if you do that and it still doesn't make sense, like, well, let's say you didn't have a single proton present, well, then you'd have to make it 2 and then double everything else again. Okay, so that's kind of the process you want to approach or kind of go with it. How would you distinguish between these structures? So they all look very similar. So think about how you might do that, and then see if it matches what I say. So the way that this is going to be different is this first one right here. It has CH2 that's directly next. That's basically the carbon directly adjacent to the oxygen on the ester. And so you're going to be adding 3 ppm to that CH2 that is a singlet, right? This right here is a CH2 that is a singlet, but it's only adding, we're not adding 3, we're adding 1. Okay, so that's a big difference. And that's how we're going to be able to tell. Other than that, these are going to be coupling with one another. These are going to be coupling with one another. You'll also notice the chemical shift of this CH2 right here is going to be much farther downfield, and it's going to be a triplet. This is also going to be a triplet, and then this is going to be a triplet, and this is going to be a triplet. So your triplets are going to be in different locations, and then your singlets are going to be in different locations as well, even though your splitting patterns are still all the same. Okay, so that's really what the key to these differentiating between these is going to be. You want to look at the chemical shift difference. Okay, so same thing applies here. This is 9 hydrogens, right? This is a singlet, but there's 9 hydrogens here, and it's also a singlet. Just the location of that singlet is going to be different, right? This should be more downfield because it's next to that oxygen, okay? And then same thing for that. We have that singlet for 3, and then we have that singlet for 3. We do have the nice number where we were talking just like above. The CH3 next to a carbonyl would add 1 ppm versus the CH3 next to this ester oxygen is going to add 3. So that's your difference, the location of that singlet. That corresponds to 3 protons at least. So this one right here, we have a proton there, 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 and there. The biggest one here, that's going to scream out the substitution right here, is this would be a singlet, and this one we don't have any singlets. They're all doublets, or there's just 2 doublets. So these are the same, and then these are the same because we have this plane of symmetry right there. Okay, There's no symmetry whatsoever in this one. So we're actually going to have 4 signals versus 2 signals as well. Okay, that's another key. Okay, so this right here, this is called a para substitution. And substituted. So whenever you get an unknown, you're going to be stoked if you get para substituted, because it shows up as a doublet for I told you there's 2 of them, right? And then we got another doublet. And and then this is going to be like around like 7 to 8, right? And so anytime you have protons in the aromatic region, you're stoked about it because you know it's a benzene ring. But then also, if you see 2 doublets, you know it's para substituted, and you're stoked about that as well. Versus like this is called meta substitution, or if you have ortho substitution, which would be like right here and right here, right next to each other. Those don't have any symmetry, and you have 4 resonances that are kind of complicated for each of them, and it's not super helpful. But if you got para substituted, you're stoked. Okay, let's go. Almost done, y'all. I thought through working through the problems that I do, or the way I do, I thought that maybe this would be helpful to approach it like this. So I put it into words. Written word at least. So look for the benzene, because that's, if you have an unknown NMR structure, if it's in around 7, then you're stoked. Again, like I said, you got a benzene ring with something on it, probably, because they're not just going to give you benzene. It's too easy. Look for the number of unique proton signals after that, and then of course, like we're talking carbon as well, but look at the splitting. If you have your number of unique signals and your splitting pattern, then you can draw fragments based on the info above and then the chemical shift. So the fragments would be like, okay, well, it's got to be looking like this versus maybe like CH2 with like an H on the end, or something like that. Like it's only part of a molecule is what I mean. And the reason why you're using the splitting pattern is because it's like, okay, well, if it was 3 protons and it was a singlet, then nothing can be there, right? Can't be another proton. So it has to be either another atom, or it could be a carbon with 4 bonds. So that is not a proton. So that's what I mean by draw your fragments. And then the same thing was like with benzene too, right? Where we have, if it was para substituted, then we know something's coming off that way or whatever. The chemical shifts, again, are helpful because it goes without saying. And then after you draw your structure, you have a proposed structure, you want to see if it makes sense. So double check all the multiplicity, double check the approximate chemical shifts, and then double check your IR and mass spec if you're given that as well. Other than that, I don't know. Hopefully this helps. Let me know. Okay.